Radical functions, which include mathematical expressions involving square roots, cube roots, or any other kinds of roots. They are practical tools in solving real-life world problems and probably in the fields most notably for politics. They help model situations where growth or change happens at decreasing or increasing rates, such as population statistics, funding allocations, or tax calculations. One most notable example for radical equations or function is ax is equals to 30 square root of x plus 5, which could represent how much funding the government allocates for building shelters after a worldwide or citywide disaster. In this equation, ax is the total funding, x is the number of people, and 30 is the base funding rate, and 5 is a threshold that ensures funding only starts when the number of people exceed 5. Now, let's consider how this function works. If 1,000 people need shelter, we substitute x in 1,000 into the equation. Adding 1,000 to the threshold gives us 1,005. Taking the square root of 1,005, we approximately get 31.702. Finally, multiplying this by the base funding rate of 30 results in 951.060 in total funding. Similarly, if we need to calculate or escalate to 1 million people, the equation shows the funding amounts of $30,000. After performing the same steps, this gradual growth in funding reflects how resources are scaled according to the number of people in need, ensuring fairness and efficiency. Graphically, this function would look like this. This function starts at 0 funding when x is equals to -5, which represents the minimum threshold before funding begins, and that is why our domain for this function is equals to -5 to positive infinity. In real-world terms, the practical domain should be x greater or equal to 0. Since negative numbers of people aren't really possible, the range includes all possible funding amounts, starting at minimum and increasing as the number of people grows. That is why the range for this function is 0 to positive infinity. The intercepts of the graph also tells a story. For our x when it is equal to -5, the funding is 0 or our y, representing the cutoff point where no funding is allocated. That is why our x-intercept is -5 and 0. For our y-intercept, when x is equal to 0, the government provides initial funding of about $67.080. And this $67.080 is our y, which is the square root of 5 multiplied by 30. That is why for our y-intercept is equal to 0 and 67.080. Understanding the inverse of this function adds another layer of insight. The inverse essentially answers the question, how many people can be supported by a given amount of funding? For example, if the government allocates $951.060, dividing these amounts by 30 and squaring the results gives us the original number of people, 1,000 in this case. The inverse function highlights the flexibility by radical functions in solving different types of problems. When we analyze the shape of the graph, we see the funding function is always increasing. It grows more slowly as x becomes larger, reflecting the square root's nature of slowing growth over time. The function has no relative maximum or minimum points beyond the starting minimum at x is equals to -5. But this simplicity makes it a good model for situations where growth continues without bounds. In simpler terms, this radical function helps us understand how resources are distributed based on needs. It ensures funding starts only when enough people are affected and grows proportionally, though at a slower rate as the numbers increase. By combining mathematical concepts like intercepts, domain, range, and inverses with practical interpretations, we can see how math supports critical decision making in real-world scenarios like disaster relief.